Hello, calculus fans. Okay, so we're constantly creating some new ways of creating derivatives. So before this chapter, we did it using a limit. Now we're coming up with some shortcut rules. So let's look at a couple of new shortcut rules that will be very helpful to us. So here's the constant multiple rule. This one's based on a limit law. In fact, several of these are going to be based on limit laws. This just says that if you have a constant in front of a function and you want to differentiate it, you can bring the constant out in front and then differentiate the function. This will be useful for us all the time. In fact, we're going to end up using this a lot, and after a while we won't even remember that we're actually using it. So let's actually prove this now. So for the setup, we're going to define a new function, g of x. G of x is going to be c times f of x. Keep in mind that c is just a constant. It's just a number. Now we can write out the derivative of g of x by using the definition. So g prime of x is the usual sort of limit that we write down. Now g is c times f, so we can replace that in here. And what we're going to do now is factor out the c. This is just a multiplicative constant. So if we factor out the c, it should look something like this. Notice that the c is in both of the terms in the numerators. That's why we can bring it out of the whole expression. Now here's the key step. The key step is that we pull the c out of the whole thing, and this is using one of our limit laws that says that if you have a constant and you're a constant multiple of something and you take a limit of that, you can bring the constant out in front of the limit. Now I don't remember that this was limit law 3. I had to go look that up. If you were to cite something like this, I would say we're just following one of the limit laws. So now, at this point, here's the key thing, is that what's left over here is the definition of the derivative for f of x. That means the thing that I have circled here in red is just f prime of x. So we've proven that the derivative of g of x is equal to c times f prime of x. And that's actually what we wanted here. The thing that I have circled in blue, that's c times f prime of x. Notice that we're switching between the Lagrange and the Leibniz notation, and you want to be used to being able to switch back and forth between those two. Okay, let's use our new rule, this constant multiple rule, to compute a couple of derivatives. And we're going to be using this constant multiple rule in conjunction with the power rule that we had just talked about. So in part A, if we want to take the derivative of 7 times x to the 9, the first thing we'll do is pull that 7 out in front. That way, on what's left over, the derivative of x to the 9, we can just use the power rule to get 9x to the 8th. And then the whole thing combines to just 63x to the 8th. Okay, so that's not too bad. Now let's do the second one. We're going to compute a derivative of negative 0.5 cube root of x. Now the first thing I want to do is rewrite that cube root of x as x to the 1/3 power. That's generally going to be easier to work with. So that was just an algebraic rewriting. The first step that we're actually doing something is here where we pull out the negative 0.5. That's, again, using the constant multiple rule, because if you have a multiplicative constant, you can bring it out in front. Then all we have to do is differentiate x to the 1/3. So that's where this piece here turns into this using the power rule. So remember, the power comes out in front, and then we subtract 1 from the exponent. So the exponent turns into 1/3 minus 1, and that's how we get the negative 2/3. You might also notice that I changed the negative 0.5 into a fraction. And that way, in the end, when we combine these, we get this as our final answer. Negative 1/6 x to the negative 2/3. So we used a couple of things in both of these problems. We used the constant multiple rule, but we also used the power rule to help calculate these derivatives. Okay, that's all for now.